Yes, so I wanted to present our, so to say, sister project SOLER to this group also. I just have to find out a way to get rid of one of the panels, which is on the way. Okay, now I'm fine. So I will give you a project overview, and I will start with the teams. So I will basically, you see the logos here, and I will show you who are the people who are working in the SOLER team first. So the University of Turku is the coordinator, and we have the usual suspects from our group working on this project: Nina, Diana, Jan, Christian, and Immanuel. In addition to me, and Terhi Jokilehto is our project manager. And in addition, we have contributions from several students who are on grants and internships, so they are not paid from the SOLER project, but give like a in-kind contribution. In the University of Helsinki, we have 3 key people: Emilia Kilpua, Jens Pomell, and Daniel Price. In the AIP, we have Alexander Varmut, Jake Mitchell, and Christian Fox. And then in the University of Graz, we have Astrid Veronique, Karin Dissauer, Markus Baumgartner-Steinleitner, and Robert Jarolim will join the team once he gets back from the States. Currently, he is acting as an external collaborator. And then finally, Paris Observatory, we have Karim Briand, Baptiste Cicconi, Julien Girard, Alain Lo, and Jing Chang as the team working in Paris. Well, these are the people who are working in our project, and the project idea in brief is that we will investigate the most energetic phenomena occurring at the sun, their interrelations, variability, and energy partitioning. And the idea of SOLER is different from Spearhead, mostly in that we are putting more emphasis on what's occurring at the sun during solar eruptions. So the newly expanded, unprecedented heliospheric spacecraft fleet will of course now provide us with unique opportunity to investigate the energetic solar eruptions as well, not only particles. And we have 3 perspectives. The CMEs, we pick fast CMEs greater than 1,000 kilometers per second speeds, strong X-ray flares larger than M5 in GOES classification, and large SCP events, which we define the same way as traditionally already in Serpentine. We used this definition of more than 25 MeV proton events as the large SCP event definition. And we aim at making progress in understanding how the eruptive phenomena are linked to each other, how they are interacting with each other, and then how they result in acceleration and release of high energy particles from solar corona into IP space. And magnetic connections of sources and large amplitude coronal waves and shocks related to these events will also be investigated. So not only the active regions themselves, but the global coronal phenomena related to these things. SOLER will provide a wider scientific community, a broad array of advanced data products, and many novel data analysis and visualization tools like Spearhead. So it's not only about the science, it's also about the tools and data sets that are generated and made available to the public or to the research community. We have scientific objectives to answer 3 science questions. One is about the connections. So what are the magnetic connections between electromagnetic radiation sources in the low corona, usually observed in X-rays, and the high corona, where we are usually using radio, and how are they connected to the particle radiation that we can observe in situ. Then the relations, what are the relations between the properties of the in situ SCP observations, energy spectra, time profiles, anisotropies, composition, and source characteristics, flare X-ray spectra, time profiles, composition, shock parameters, all these, and what are and between the source characteristics themselves. So all kinds of relations, how these are coming about. And then the variability. So typically when we correlate these relations or make correlations of these relations, we can see that there's quite a bit of scatter still. So what are the reasons for the large variations in SCP properties and the associated flare and CME characteristics? So we cannot really say that we would have very simple correlations between the parameters, and we would like to understand a bit more what are the reasons for the variability. And the technical objectives are, we have 3 of them as well. So we will produce catalogs. We will deliver 3 interlink catalogs, so 1 for flares, 1 for CMEs, and 1 for SCP events, and we will interlink them so that we will know which are linked to one another. We will have analysis tools that we will provide, visualization of solar eruptions, for example, or data sets, and some modeling results as well. And then finally, the data. We will produce several high-level multi-instrument datasets and distribute them openly to the scientific community. So pretty similar what we already did in Serpentine, and of course quite similar to what is going to be coming from Spearhead as well, but the emphasis now is on different data products than in Spearhead. So if you put them in a one sort of graph like this, the connections are about the magnetic connections that we can, for one thing, have in the coronal part of the heliosphere, and then of course the global ones. The relations, how are the different phenomena of a solar eruption or energetic solar eruption related to one another, and then this variability, that all these type of correlations between different quantities contain a lot of scatter, and it would be great to understand a bit better what are the reasons for this. So our project is divided in 9 work packages altogether, and basically we have analysis method work packages. These 5 work packages that we have here, up to 6, they are developing analysis methods. And then work package 7 is the work package which sort of aims at bringing everything together, so applying the analysis methodologies in the analysis of solar eruptions. And then finally we have the dissemination, communication, and tools and data distribution work packages, which are then delivering these results to the community. And we hope to get feedback also, not only provide results, tools, and data, but also get some feedback or requirements, and of course collaboration with the community as well. And this is one of the big reasons why it's important that you guys are also aware of the project. Here's how what type of datasets we are going to be using and in which work package. So you can see that X-ray observations are handled in work package 3, and there we have several types of observations. So light curves, we have spectra, and we have even imaging observations. And then radio observations, those are analyzed in work package 2. Work package 4 is dealing with all kinds of things like coronal waves, for example, also magnetograms and different types of other EUV and optical structures in the corona. And work package 5 is the in situ data work package, and then work package 6 is the modeling work package, where we are trying to understand, based on modeling, a little bit better the coronal magnetic fields and the plasma in the corona and inner heliosphere as well. So the schedule and milestones is here. So you can see that we have these data analysis methodologies developed during the first 2 years of the project, roughly. Work package 6 runs half a year longer because of some personnel constraints in GRAS, but in general we aim at having, at the end of the second year, all of the methodologies ready. The scientific analysis of energetic solar eruptions started a little bit later than the other work packages and will run until almost the end of the effort, and then these tools and data distribution and dissemination, communication, and exploitation are the ones that are running the whole project. The orange arrow here shows where we are right now, so we are in month 18, and our first 3 milestones are now completed. And I will show next a couple of things. So from each of the work packages here, these from 2 to 8, I will show some highlights, not really based on anything else than my sort of let's say personal picking of them, based on the input that I got from the work package leaders. So in radio data analysis, maybe the most important product so far is this NenuSun facility, where you can access the Nenufar data and other radio data related to each date when we have good observations coming from Nenufar. So the interface is such that you can pick a date, and then it opens a window where you can see how the data is looking over that day, and you can have the radio data and some context observations also in this. So this is a way to assess the radio observations of each of the dates quite nicely. On the X-ray data analysis side, so far the main effort has been to develop this SunKit specs, a Python package for solar X-ray spectroscopy, which is done in the AIP. And this is something that will make it easier for, let's say, modern Python users to do this type of spectral analysis of X-rays in solar flares. And we expect to carry out also some studies of ourselves and do this type of sort of proof of concept studies with the tool. There is optical and EUV data analysis tools, and let's say the first one that we can offer so far is the SOLER wave tool. This is a nice tool, so you can analyze how the waves in the corona are propagating based on JMaps. So you can use this type of sectorial splitting of the solar surface, spherical solar surface, and you can track how EUV waves are propagating in these sectors away from the central active or the erupting active region. And you can see that you can spot the wave quite easily in these JMaps in these sectors, and then also perform wave kinematics analysis, so getting the distance of the wave peak and wave front against time, along with the mean speed, wave width, and wave amplitude. So this wave analysis can be done quite nicely with this tool. We have in situ data analysis tools, mainly concentrating on energetic particle data, but we have this type of multi instrument panel plots now, which can be made. So you can include also magnetic field data, plasma data, and even X-ray data, hard X-ray data into the or even partly soft X-ray data, so STIX data basically here. So light curves can be put into the same panel, and you can generate useful plots for your energetic particle event analysis. And we also have made some novel type of tools for onset analysis. So these are complementing our earlier methodologies that have been developed based on the Kusum method. And these are now the regression methods. So you can basically let the tool represent the time intensity profile in this piecewise linear or a log linear basically, so the logarithm. So it's basically piecewise exponentials that you are seeing here as the evolution of the event, and then identifying the first one here will give you an idea when the event is actually starting to increase over the background. This is something that we are currently testing, and the idea is to compare this with other methodologies to investigate whether there are some sort of systematics here that would be interesting to take or important to take into account. The simulation methodologies are concentrating on two things. So we have this, as I mentioned, this magnetic field modeling. The first method that was developed is the magnetofrictional method from the University of Helsinki, which is a very computationally efficient, time-dependent modeling of coronal magnetic fields based on the magnetofrictional method, where the Faraday's law is implemented so that you have the Ohm's law, and instead of the true velocity field, what you are using here as the velocity is something that is related to the currents that are flying in the system. And this is a way to relax the magnetic field into a configuration that can even be changing temporally. So the boundary condition on the bottom can be temporally changing. Another thing that we have been developing is a modeling tools for coronal particle acceleration, and we are making this type of modeling tools. The tools are such that this simulation happens to be still a local one. So you set it up in the corona using your coronal conditions around the shock. You determine a few of the shock parameters, and then you can run a population of electrons through this system. What we include here, which is novel, we include not only diffusive shock acceleration and shock drift acceleration, but also this stochastic shock drift acceleration, meaning that we can increase the scattering frequency of the electrons near the shock front and obtain various types of spectra, and also identify beams, for example, which can help us to assess the ability of the shock to produce type 2 radio bursts, for example. This is called EASY, and we are going to soon make it openly available in GitHub. In the scientific analysis, so far we have been doing two things, or two main things. One is this SOLER event catalogs, which are underway. So flare catalog will contain flares observed both by STIX and GOES, and CME catalog will contain CMEs faster than 1000 kilometers per second observed by LASCO, and then the GOES flares and LASCO CMEs are already linked, and the STIX flares will be the ones that will be linked next to the CMEs, and SCP catalog is currently being populated as well. So that was the 25 MeV proton catalog. What is different from Serpentine? In Serpentine, our catalog was concentrating on multi-spacecraft events. Now we are also including events which are observed only by single spacecraft. So it will be a little bit larger catalog in the end, or quite a bit larger catalog in the end than what we had in Serpentine. SOLAR event studies are concentrating on finding out different types of connections between the observed phenomena. And the first energetic solar eruption case study we completed earlier this year, led by Diana Morosan. And we can show the temporal associations and magnetic connections between the CME shock and accompanying radio bursts. Notice that we had also imaging observations of the radio burst this time, so we could find out where the radio burst was generated at the CME shock, and making a connection to the in situ observations allowed us then to make important inferences on the acceleration of the electrons in these eruptions. Finally, the tools and data distribution work package. We have the Jupyter Hub server that makes delivered tools freely available to use without installation. So we have so that is the hub is such that we can basically do these type of or you can run our tools without installing them in your own computer. So all you need is a GitHub account, and with that you can register. We have the project GitHub makes all codes freely available to use, and you can also contribute to these tools. And then finally, the data and other project output like catalogs will be freely available in Zenodo. And you can use the QR codes here to access all of them. And finally, if you want to know more, join our user workshop, which will be available. It will be conducted in hybrid mode. We will be meeting in Paris Observatory next week from Monday to Wednesday, but we will also provide a possibility to follow the meeting online. Online registration is open now until Friday, end of business. Here is a link. Jan can put it to the chat, so you can quickly register if you want to come. You can register on each of the days separately. No need to be present all of the time, of course, but we need this registration simply to distribute the links to the participants that are interested in the meeting. We will have the first afternoon, Monday afternoon, devoted for science talks. Then we will have some demos of the tools on Tuesday morning, and then hands-on exercises in the afternoon session, trying to make them so that it's possible to follow these hands-ons also, or perform these hands-ons also in the remote mode. And then finally, we will have some discussions during the last day of the meeting, future science collaborations with the community. So in the registration form, we have a possibility to propose some sort of discussion topics. So if you are in particular interested in something concerning SOLER, you can easily propose a topic to be discussed here, and we will select some of the topics proposed by the audience, of course, also for discussions. And finally, the feedback session. This is the feedback session mainly devoted to the tools, but of course also if you have any other types of feedback you want to give to the project, there will be a full 1.5 hour session for the discussions in the end of the meeting. Okay, thanks for your attention.
Thank you, Rami. Okay, we have a question or comment by Bernd first.
Yeah, thank you very much, Rami, for this interesting workshop presentation or things like that. Would it be possible for you to put the thing onto our Google Drive so that we can, for example, I can take it to Kiel so people can join in this SOLER user workshop, although they don't know it by now?
Yes, I actually, or Jan submitted the slides already to the correct place. I'm not sure whether that was the Google Drive or whether it was in the data distribution system of the. But the slides are available there, and as said, I can also, and I think I already did, so I put it to this link also to the SOLER All list. So if your guys are registered in, the Spearhead All list, so if your guys are in the Spearhead All list, they should have received this. Just the confirmation, by the way, did you guys receive the email yesterday?
Spearhead All, I received that.
I think that's something because I don't receive. I have to ask Mattia all the time.
Bernd doesn't receive Spearhead All.
You don't receive
No, I
that?
didn't receive anything.
We had some problems with that. So, Alexis.
Hi, Rami. I have a question
Hello.
about the easy code.
Yes.
It's a funny name for shock acceleration, I think. But can we actually specify the magnetic field through which the shock is propagating?
At the moment, yes, you can of course develop a more complicated model yourself. So at the moment we have a hyperbolic tangent profile through the shock, so you can specify the obliquity of the far upstream field and the compression ratio, magnetic compression ratio, and then the width of the shock, and those will be then used to generate you a sort of a magnetic hyperbolic tangent profile for the magnetic field magnitude, which is consistent with Rankine-Hugoniot. So this is relatively simple. We don't have things like overshoots at the moment, but those are on the to-do list so that it will be easier to do. But the problem, of course, is that once you start messing with something that is not consistent with Rankine-Hugoniot, then it should also be temporally dependent to be consistent. So that's why at the moment we are limiting ourselves to something that is sort of consistent from the point of view of physics.
And is there a way of reproducing the work we did with Shirley, where electrons that are trapped on loops may be re-interacting with the shock?
At the moment, this is just a local 1D code. So at the moment, we do not have a global magnetic field geometry. This is also on the to-do list, and it would be possible in the future, I hope. But at the moment, we are simply providing a code which could be integrated with MHD simulations to look at the local beam generation of the electrons to understand where the type 2s are originating from.
Okay.